So an example doing some pre-widening in R, basically I will set a seed to be able to reproduce this thing here. I will simulate an ARIMA 1,1,0 model with just an AR part to be my X. So this is my input signal. It is indeed correlated. Then I will take that, let me just do that, shift it backwards 3 and 4 steps respectively, and then I'll take Y as my output to be a sum of, say, this constant plus some weight on the lag 3 and lag 4 inputs. So then we get an output that looks like this. Basically, when you just look at it, it looks just scales, but that is the output. Notice that in this case there's no noise here. However, if we want to look at the cross correlation function between the first data set, namely the true input X, and the output Y, it looks like this. So it's very difficult to see what is actually happening here, because what we're masking is the autocorrelation between, for X, let's just plot that. So since the X process is non-stationary, it goes very, very slowly to 0, and that's why we get these fat tails when you look at the cross correlation. So we need, in order to make a model for X, we need to differentiate that. Let's look at the autocorrelation function of the lag 1 difference here, and you see that goes exponentially to 0 very fast. Let's look at the partial autocorrelation function. Here we see that only lag 1 is different from 0. It's almost 0.7, which was the true value that we used. So let's just fit an ARIMA 1,10 model and see what we got. We got an estimate here of 0.63 with an uncertainty. That means that the true value is actually inside 2 times the standard error, so that's basically fine. As mentioned before, when we pre-widening X, what we basically do is that we just take the residuals. So those are the residuals. Then I'll take the coefficient here, that's the estimated coefficient out of the model here, and now I use that to filter Y with the same model. And now you just have to think of what is this model here. Well, what we wrote was that it was an AR1 process, 1. Now I have to use whatever notation. No, I use the R notation to that minus on the left-hand side, B, and then a nabla on YT equals epsilon T. So that's the process that we used as input. And if we do the multiplication here, then we have a 1 minus phi B times 1 minus B. That's this thing here. If we multiply this out, then we get a 1. And then for B of the first power, we get minus 1 plus phi. And then we get a plus phi, B there, phi B to the second power. So that's what we have. And those are actually the coefficients that I have here for my filter. So let's now, maybe we should just plot the pre-widening of Y here, just so you can see how it looks like. Now, instead of the signal we had before, now we have something that looks much more white noise-ish. Let's again plot the cross correlation function between the two. Now I did not do it. Now I just did for those two, and you can see that you have a signal in lag -3 and lag -4 as expected. We can also do a columbine of the two processes, and then we get the same as before, where we have the autocorrelation in diagonal, and then if you combine the two off diagonal, then you have the cross correlation there. So to fit the model, what we have is we want to have Y, and we have had the lag 3 and lag 4. we can do that. In this case, we can just use LM to fit a linear regression model on this data here. And if we do the summary of that, well, first thing to notice is we get a warning because essentially perfect fit. Everything is significant. There's virtually no standard error because there was no observation noise in here. So this was very artificial, and if I want to estimate this in ARIMA, it just fails because it cannot optimize things when there's no. So let's add some noise to make it a little bit more realistic, but still uncolored noise. So the lines that are coming out now are the same as before. I'll just plot Y again. Now what I'll do is I will just add some white noise to it and add that. You can hardly see the difference when you look at the plot between the black and the red line here. And then again I will look at the cross correlation between Z as the input and the output. And again we see, due to the fact that X is non-stationary, we have these. You can see that there's something happening around some negative lags here, but it's very hard to say anything about it. So now the procedure is the same as before. The X input is the same, so we don't have to pre-widen that. We don't have to estimate a model for that because we know in this case what it is. But we do have to pre-widen Y again. It's the same filter on the new data. And again, it looks pretty much like just some noise. And let's look at the cross correlation between the pre-widen X and pre-widen Y, alpha and beta in the slides. Again, we see a signal in like -3 and like -4. Again, let's combine it. And this time we can also do a linear regression model. And here we do not get a warning. We get a residual standard error that is close to the one that we used. So everything here is fine. We get estimates of the coefficients that are close to the true value, 15.8 and 1.5. So things are nice. Let's estimate an ARIMA model. Again, here we don't have any structure for the noise. We just use XREC with the lag3 and lag4 coefficient and then an intercept. And we get effectively the same estimates, not exactly the same, but effectively the same estimates. So when noise is uncolored, everything works fine. But now what we'll try to get to is a case that is more like the intention here. When the noise has some color to it, then it's not as easy. So the noise now will be simulated ARMA noise here with an AR coefficient of 0.8 and MA of 0.7. And again, if we plot Y, it looks pretty much like what was there before. And if we look at the cross correlation between the input and Y, again, it looks pretty much like what we saw before. Now we'll start to do the pre-widening, and again, the first steps for X are the same because we did not change X. We will pre-widen Y again. And look at that. Again, it looks somewhat similar to before. And let's look at the cross correlation now after pre-widening. So what you have to kind of appreciate is before pre-widening we had this cross correlation. After pre-widening we get this. So all of a sudden again we can see that we have like -3 and like -4. As an alternative, I will show you how to use the forecast package to do the filtering. It has a function called ARIMA with an uppercase A, where you can specify a model as argument, so it does not estimate a model, it just uses this particular estimated model to do this. And let's just look at the plot of the pre-Y data. Oops. It gives you the inverse root to give you plots the model that we estimated here. What we care about are the residuals from this pre-widen, so it's a little bit different from this. What we want to plot for comparison are the residuals. And again, we look at something that is much more stationary than what we were looking at before. Let's look at the cross-correlation function once again of the here, and we see this lag 3 and lag 4 as we've seen so many times before. And once again, I will just show you, if you use the ACF and give that argument as 2 columns, it will give you the autocorrelation function in the diagonal, and then it will give you in the off diagonal, it will give you the backwards and forward in time for the cross correlation. It also goes for higher dimensional systems, but for now it's just a 2-dimensional system. So again, lag -3 and lag -4, that's where we have to pay attention. We will do the same model as we have done now a number of times. Still, everything looks nice and significant here. What I tend to do, I skipped it the other times because we knew everything was perfect. But now, if we look at the traditional residuals plot here, residuals versus the fitted values, it looks quite fine. Also, the QQ plot looks reasonably okay. And when we look at the scale location plot, it's also almost horizontal line. And finally, to look at the residuals versus leverage, everything is fine. The highest leverage is 0.05. So basically, there's not much to say here. What is often forgotten is to look at the autocorrelation of the residual. This should be white noise and independent in order to fulfill the assumptions for the linear regression model, but indeed it is not. So let's try to fit an ARIMA model. We know it's a 1,1 model. We don't spend time on figuring out what is the model, but just estimate this one here and look at the diagnostic plot for this. We see that, well, there's no significant autocorrelation left, and the noise or residuals here looks like white noise, so we are fairly happy. Now, if we look at the coefficients that we estimated here versus the coefficients we estimated when we did the linear regression model, let's just compare for 1 second. I think now we can see them all. So what we get here for an estimate of the intercept, 15.97, that's pretty much the same that we got up here. When we look at the estimate for the lag 3 coefficient, we got, with the ARIMA model, we got 0.82, which is very close to the 0.8 that we actually used. But for the linear regression model, we get 1.05. So that's a totally different value. The uncertainty is sufficiently large, but also 3 times larger down here than what we have up here. So it means that the true value is still inside the prediction or the confidence interval for this. And if we look at the lag 4 coefficient, which was 1.5, again, it's inside here. And down here, it's just about on the border of 2 times the standard error. So it's actually very close to the fact that not having the true value inside the confidence interval down here. And again, the uncertainty for the linear model here is much greater than doing what is more adequate. So when you have things that are sampled in time, and if there is autocorrelation of residuals, you should try to build a model that takes that into account. That's the take-home part of this, and that's, you can say, what to give you just as an example of what pre-widening can do in order to show you what is the difference between the cross-correlation of the input and the output before and after doing pre-widening with a good model. So what we did previously was to have this structure over here, but what we will try to add now is, what if we know some more about the noise structure up here? So if we have an ARMA model up here where we have a theta of B over phi of B, and then we have some white noise input here. That's basically what we call a so-called transfer function model. It's also in literature called Jenkins, as they've been doing a lot of work on these. And we can, of course, extend this to have multiple inputs here. You can see the book for an example on that, but that's just, you can say, making life more complicated. For doing examples, this is sufficiently complicated. And if we look at some names of this, then we have so-called finite impulse response models. We have the autoregressive models with exogenous input. We also have the AMAX models, autoregressive moving average models with exogenous input, sometimes also called output error models, where you don't have any model for assumption for the observation noise. And basically, for what you want to do for this class of models here is that you want to use XREC, if you're using ARIMA at least, to say how can I estimate the coefficients down here, where you use the ARIMA function to estimate the top part here. So how do you identify these transfer function models? Effectively, you're looking at the impulse response being potentially infinite. What we just saw before was we can use pre-widening to get an estimate of the structure similar to of the system, h of b, and then based on this we can get an estimate of what could it be that we want to estimate. Now when we then specify everything, then we can estimate parameters in the particular model order. Just to get an idea of what is going on, you can, for some particular structures, one tool you can use to play with things is the MATLAB toolbox called ident. And I'll just show you some examples for some transfer functions here. In this case, you have two real poles, and what you expect to see is kind of a two-phase exponential thing here for the impulse response, and you have the step response here that's just going towards a level there. Now, if you take the two poles and rather than having as being just real, and just make them complex conjugate at a pair here, then you see an impulse response that has a sign on top of the exponential damping that we had also on the previous slide, and the step response also give you a damped oscillation around the true value. Now, if we add more complexity to it, in this case a couple of zeros as well, but we add both complex pair and a real pole here that is the one that has the closest to unity, so that's the one that dominates. So we have the exponential here, and then you have an oscillation on top of that. And you can do many more examples of that yourself. So what you have to do is basically, first you have to identify a structure for the model for this. Then based on this structure that you estimated, then what you do next after estimating this structure is you then subtract and look at the residuals n here, and then you start identifying an ARMA model for this, finding the phi and theta polynomials, and then when you have the full model, then you want to specify all these things and estimate that in one go. And the estimation is pretty much like all the previous estimations that we've made. You look at one-step predictions, and then you treat the input as known, also in the future. If it's stochastic, then you just condition on the observed values, and then you just calculate the sum of squared prediction errors, and you want to minimize that and find the parameters that do that. If the epsilon t is white noise, then you can do the maximum likelihood as well. Gives you, at least in that case, it gives the same as the least squares. If you have a finite impulse response model or an RX model, then you can write it as a linear regression model, and thereby you can use that also to solve. You can also do moment estimates, which I will, as said before, generally not recommend if you have other options, but you should, if you do that, you should match the lowest order lags to the estimated impulse response and take it from there. Basically, these are output error estimates. So to look at validating this, you pretty much do the same thing as you did for the pure ARMA models. What you have to do as well is to test the cross correlation, and as mentioned before, the variance is 1 over n. If one of the signals is white noise and they are uncorrelated. And you can also do the Young-Box or Ponton-2 test to test for the dependent structure and the cross correlation structure.